Hello everyone, so welcome back. Now we have a small topic left in this chapter before we go to the Van de Graaff generator and then the chapter is over. So we are going to see about capacitors in series and capacitors in parallel. Just like how you learned about resistors in series and parallel in grade 10. So when you have a resistors in parallel R1 and R2, the effective resistance in series is given by R1 plus R2. And for a parallel circuit, it was given by 1 by R equals 1 by R1 plus 1 by R2. In the case of capacitance, it's just the opposite. That is, if it is series connection, where the capacitors are connected in series with C1 and C2 capacitances, then the effective capacitance of the circuit is given by 1 by C equals 1 by C1 plus 1 by C2. And if the capacitances are connected in parallel in this manner, then the effective resistance is given by C1 plus C2. So it's just the opposite of resistors. But let's see how is this true. The derivation for the series and parallels. So let's first look at capacitors in series. Let's say you have, we can assume n number of capacitors, but let's just start with two capacitors. So we have capacitance 1 and capacitor 2 connected in series across a battery with voltage V. So you have to be sure that make sure that in series the properties what you learned in grade 10 still remain the same. That is, the same amount of current flows through both the elements over here, and the voltages are different in series. So this voltage is not the voltage in the formula C is equal to Q by V. This voltage is different from the effective circuit voltage. So you have to keep in mind that this is not the voltage for each capacitor, it's the total voltage. So also we know that in a series circuit, the sum of the individual voltages equals the total voltage of the circuit. This is a property of series circuits. So we have the total voltage of the circuit of the battery equals the amount of voltage in element 1 and 2, that is capacitor 1 and 2. So we have this relationship. Now from here we start with the derivation. From the formula of capacitance, which is C is equal to Q by V, we can calculate what is V1 and what is V2. So what is V1? When V is cross multiplied, it becomes Q divided by C. So you have charge through 1 divided by capacitance of 1 plus charge through 2 divided by capacitance of 2 equals, this is the voltage of the effective, that is the total circuit. So we can consider V as, when you want to modify V in terms of the total, it becomes capacitance effective, that is total capacitance of the circuit equals to total charge equals to total voltage, which is this total voltage. I can call it over here, it's fine. So now what is VT? The total charge divided by the effective capacitance, and this is the one we need, effective capacitance of the circuit. That is why we are doing all this. So you can notice here I have written it as QT, Q1, Q2, but in reality the charge stored is the same. This is because charge is conserved. The same amount of current is passing through both C1 and C2. The flow of electrons is the one giving the presence of charge. We know charge Q is equal to IT. If the same amount of current is flowing through C1 and through C2, that means the charges must also be same in C1, C2 and the entire circuit. Charge is conserved. That means QT equals Q1 equals Q2 equals Q. The entire things are equal. So you can cancel them off. And you're left with the final expression which we require for a series connection, which is, I'll write it here, 1 by C equals 1 by C1 plus 1 by C2. This is the expression. You can notice first step is to make a relationship out of the voltage. Second step, convert the voltages in terms of capacitance using the formula C is equal to Q divided by V. And then we have to make sure that the charges are equal. The charges will be equal because charge is conserved as the formula IT. And then you can cancel off the common terms and we are left with this. This can be applied to n number of capacitors. It just keeps on adding. So we are done with series. Now let's look at parallel. Okay, so now this is the condition or circuit diagram for a parallel connection. In the previous case, we expressed voltage as a sum of two individual voltages so that we can take a relationship of the capacitance. We somehow need to bring the term capacitance into the formula. That is our objective over here. So in the previous case, we took voltage because it was easy. Sum of the voltages equals the voltage. But here all three voltages are equal, so we cannot make use of voltage. We have to do something else. So what other term from the capacitance formula can be used? So the capacitance formula has the term capacitance, has the term charge, has the term voltage. We can't use capacitance directly because that's the whole point. We are trying to find capacitance, so how can we take capacitance? Voltage in this case we can't because the voltages are equal. So we are left with charge. We have to do some relationship out of charge. If you have noticed in the previous case, charges were equal. That's because the same amount of current flew through each of the elements. But here, the amount of current passing is different. You know, current splits in a parallel circuit. That is, if this was, okay, let me change the battery. If this was current I, it would become I1 and I2 over here. The current just splits into two different magnitudes. So the charges in C1 and C2 won't be equal, but the sum of the charges will be equal to the effective total capacitance. That is, if you somehow manage to find the capacitance of this combination, and let's call it a new capacitor. How to, for example, let's say this capacitance was given a magnitude of 5 Faraday. The unit of capacitance is Faraday. So capacitance 1 is 5 farads. And capacitance 2 is 10 farad. And you find the effective capacitance, which we are going to, and you imagine this part to be one capacitor of that effective capacitance. So the circuit diagram would be modified to this way. And the reason I'm showing this is because now the charge in this circuit equals the charge in this circuit. That means the charge of the effective capacitor equals the sum of the individual charges stored in each of these capacitors. So that is the relationship we require. Q equals the total charge equals sum of individual charges in both the capacitors. Now let's convert it in terms of capacitance. C is equal to Q divided by V. So what is Q? It is equal to V times C. That is V effective, which is the battery, into the capacitance. This is the total capacitance we are looking for. You have to be careful on what terms you substitute in each of these individual charges. The effective charge will be the voltage of the battery times the capacitance of the effective circuit, which is what we are looking for. And the charge in the capacitor 1, these are just examples. The charge in the capacitor 1 will be given by voltage remains the same in parallel circuits. So it's again going to be V, but times C1 plus V times C2. V is common. So you have the final formula, which is total capacitance equals sum of individual capacitors. So this is for parallel circuit, and again you can repeat this for any number of cells in the parallel way. So here we have made use of the fact that the sum of individual charges equal to total charge stored in the circuit, and then we converted charge in terms of potentials and capacitance. And since potentials are equal in a parallel circuit, you can cancel them off and you're left with the final expression for sum of capacitors. So this is about capacitors in parallel. Okay, so this is it for this video. In the next video, we'll see about the energy stored in a capacitor. We know capacitor has to store some energy because if the battery is able to transfer the charge to the capacitor, in the absence of the battery, if you place an electronic device, the device would work. That's because this capacitance is discharging. That means it has to have some energy to do that work. to push the charges away from it inside the appliance. So that work done requires energy, and that means there must be energy in a capacitor. So let's try to find out what is the energy in the capacitor in the next video. So thank you for watching and stay tuned.